We'll start in 1 minute. We'll continue with the sample final exam, and if we finish that, we'll work on other Chapter 3 problems that I got from other instructors. The final exam is on Monday, starting at 3 p.m. Okay, the next problem is to sketch a graph of this polynomial function. This is a degree 6 polynomial, and the leading coefficient is negative 1/4. And so that means since it's degree 6, the end behaviors have to match, and since the leading coefficient is negative, x or y approaches negative infinity in both directions, so the graph will be downward on both sides. So we can identify the zeros. One of the zeros is 0 itself. When x is 0, x to the third is 0. Another 0 is positive 2 for x. And the third one is negative 1. So we'll draw an axis, two axes, and we'll label the x-intercepts. 0, 0 is an x-intercept, and it's also the y-intercept. When x is positive 2, we have another x-intercept. And when x is negative 1, we have a third intercept. The multiplicity of x equals 0 is 3, so that means we have a cross point at 0, 0. The multiplicity of 2 is even, it's positive 2, so that means we have a touch point at 2. And the multiplicity of x equals negative 1 is 1, so we have another cross point. So we can plot a few other points and make sure that we have the graph in the right place. But we know enough, since it's degree 6 and the leading coefficient is negative, and negative 1, we have a cross point. We know the graph is going to be below the x-axis to the left of x equals negative 1. It's going to cross and then turn around, and it will come back through this 0 because it's another cross point. And then it will bottom out somewhere, and then we have a touch point at 2. It will bounce off, and then the right end behavior matches the left end behavior. So we could sketch the graph based on what we know, but we can always plot a few extra points. So when x is negative 2, just replace every x with negative 2. So we get negative 1/4. Negative 2 to the third power is negative 8. Negative 2 minus 2 is negative 4, but negative 4 squared is positive 16. And then negative 2 plus 1 is negative 1. So we can see that this number is negative. A negative times a negative times a positive times a negative is negative. And it's negative 32, so that's way down there. So just as we suspected, the graph is going to do something like this. You can determine what the y-coordinate is when x equals 1. So we have negative 1/4 times 1 to the third is just 1. 1 minus 2 is negative 1, but negative 1 squared is also positive 1. And 1 plus 2 is 2. So this is negative 1/2, which is right in here somewhere. So that's what we already expected. And then we have a touch point at x equals 2. So it comes up to the graph and touches and goes back down. If you want to verify that when x is 3, the y coordinate is negative, you could do that. So why don't we go ahead? Negative 1/4. 3 to the third is 27. 3 minus 2 is 1. 1 squared is 1. And 3 plus 1 is 4. So we do have a negative 27. So roughly this is what the graph looks like. It's not very pretty, but it's good enough. Okay, the next one, sketch the graph of f of x equals negative 1 over x squared plus 2. Label all asymptotes and intercepts. Well, there's a fairly easy way to graph this and a more difficult way. The easy way is to start with y equals 1 over x squared. And then we'll have two transformations to get to f of x. But y equals 1 over x squared has x equals 0 as a vertical asymptote. 0 makes it's a restricted value, so x equals 0 is a vertical asymptote. And this function has y equals 0 as a horizontal asymptote because the degree of the numerator is smaller than the degree of the denominator. So the graph of this function for positive x values looks something like this, and for negative x values, it looks something like this. Because no matter what x value you pick in the domain, 1 over x squared is positive. Okay, then the next step would be to reflect this function across the x-axis. So sketch y equals negative 1 over x squared. So we just get a reflection across the x-axis. So the vertical asymptote is still x equals 0. I guess we could label those. We're supposed to do that. And then y equals 0 is still the horizontal asymptote. And then finally, we take this graph and shift it upward by 2 units. So now we're going to graph what f of x is. So everything gets shifted upwards. So that means we're going to have a horizontal asymptote at y equals 2. The vertical asymptote is still x equals 0. And then the graph does something like this. So we have two x-intercepts. So how do we find the x-intercepts? Every x-intercept has a y-coordinate of 0. So we can find the x-intercepts from this equation if we replace y with 0 and solve for x. So let's do that down here. We're going to find the x-intercepts. Replace y with 0. 0 equals negative 1 over x squared plus 2. And then I'm going to add 1 over x squared to both sides. So I get 1 over x squared equals positive 2. And then I'm going to take the reciprocal of both sides. That's legal. The reciprocal of 1 over x squared is x squared. And the reciprocal of 2 over 1 is 1/2. And so when I solve this using the square root property, x equals positive and negative square root of 1/2, or 1 over the square root of 2. Or you could write this as the square root of 2 over 2, which is approximately positive and negative 0.7 something, 0.7, close enough. So anyway, the positive x value, you can write it as 1 over the square root of 2, 0 for the ordered pair, and then the other x-intercept is negative 1 over the square root of 2, 0. Okay, the next page, problem 29 on the sample final exam. The function capital P of x is divided by x minus 2. The quotient is q of x, and the remainder is negative 16. Use the remainder theorem to determine the value of P of 2. The remainder theorem says if you divide a polynomial function by x minus 2, the remainder is P of 2. And we're told that the remainder is negative 16. So all we have to do is write P of 2 equals negative 16. And the next problem, number 30, consider the polynomial function h of x equals x to the third plus 2x squared plus 4x plus 8. The function h of x has a 0 at negative 2. So in other words, x equals negative 2 is a 0 of that function. Use the 0 to express the polynomial function h as a product of linear factors. Okay, so one way or another, we're going to divide h of x by x plus 2. X plus 2 is the linear factor that corresponds to the 0, x equals negative 2. And we can use long division or synthetic division. It might be easier to use synthetic division. So we put negative 2 up in the upper left corner box. Then write down the coefficients of h of x. They are 1, 2, 4, and 8. Well, we're told that negative 2 is a 0 of that function, so we're expecting a remainder of 0. If we don't get a remainder of 0, then somebody is wrong. Either the problem is misstated or there's an error in the arithmetic. So for synthetic division, bring down 1. Negative 2 times 1 is negative 2. Add these numbers. 2 plus negative 2 is 0. Negative 2 times 0 is 0. 4 plus 0 is 4. Then negative 2 times 4 is negative 8. And when we add these, 8 plus negative 8, we get 0. That's what we were expecting. These other numbers are the coefficients and the constant of the quotient. The quotient is degree 2 because, in effect, what we were doing, we were dividing a degree 3 polynomial by a degree 1 polynomial, and the quotient is degree 3 minus 1, or degree 2. So the quotient, q of x, is x squared plus 0x plus 4. And to find the remaining zeros of h of x, we set the quotient equal to 0 and solve for x. So x squared plus 4 equals 0. We can solve this using the square root method, or the square root property. So x squared equals -4, and then x equals positive and negative square root of -4, or x equals positive and negative 2i. Okay, so the linear factors of h of x, well, since -2 is a 0, the linear factor that corresponds to the 0, -2, is x plus 2. And then we have two non-real zeros. One of those non-real zeros is positive 2i. The linear factor that corresponds to positive 2i is x minus 2i. And then the other non-real zero is negative 2i. The linear factor that corresponds to that is x plus 2i. So this is what we're supposed to do, express the function h as a product of linear factors. Okay, on number 31, expand the logarithm of the square root of x to the third y. So the argument of the logarithm is the square root of x to the third y. So we convert the square root of x to the third y to x to the third y to the 1/2. Then using one of the properties of logarithms, this exponent 1/2 can be brought out front so that it's in the position of the coefficient. So it's 1/2 times the base 10 logarithm of x to the third y, x to the third times y. And in the next step, you have to make sure you're on your toes. We have to multiply 1/2 times whatever the logarithm of x to the third y is. So we're going to write two logarithms in place of the logarithm of x to the third times y. So that means we have to multiply each of those by 1/2. So one of those is 1/2 times the logarithm of x to the third, and then plus 1/2 times the base 10 logarithm of y. And we're just one step away. The exponent 3 on x can be brought out front so that it's 3 times 1/2, or 3/2 times the base 10 log of x plus 1/2 times the base 10 log of y. So that's what we get when we expand that. Okay, the next one we do the opposite. We have an expanded expression in base 4 logarithms. So in the end, we want a single base 4 logarithm with a coefficient of positive 1. So the first step, move the coefficient 3 to the exponent in the argument. So this will become log base 4 of the binomial 5x plus 1 to the third. And then we apply the same property to the other one. This one will be minus the base 4 logarithm of x plus 9 to the 1/2. But if you raise something to the 1/2, you can write it as the square root of whatever that thing is. So we'll write it as minus log base 4 of the square root of x plus 9. This should have a bracket. Okay, now there's just one step. Since we're subtracting one base 4 logarithm from another base 4 logarithm, we can write it as a single base 4 logarithm. And in the numerator of the argument is 5x plus 1 to the third. And in the denominator is the square root of x plus 9. Okay, so that's the complete compression of that. Okay, problem 32 is next. consider the function f of x equals x plus 1 quantity squared with the domain from -1 to positive infinity. So if we didn't have this domain restriction, in other words, if we were just looking at f of x equals x plus 1 quantity squared, then this would not be a one-to-one function, because we know that its graph is a parabola. But with this domain restriction, we're only allowing x values from -1 to infinity. With that domain restriction, this is a one-to-one function, and it has its inverse. Okay, so let's observe a couple of things that will help be helpful. When x is -1, when the domain value is -1, the range value is 0, because -1 plus 1 is 0, and 0 squared is 0. And then after that, after -1, the domain values only get larger. And so the range of this function is from 0 to infinity, because whenever we square x plus 1, we always get a number that's not negative, and the smallest that it could be is 0. So that's a useful observation. The range of f of x is from 0 to infinity. Okay, to find a formula for the inverse, we go about it the same way. Replace f of x with y, so we get y equals x plus 1 squared. Then interchange x and y, so we get x equals the binomial y plus 1 squared. And then we're going to use the square root property. We want to solve for y, but y is inside this binomial squared. So when we apply the square root property, the question is, well, y plus 1, is that the positive square root of x or the negative square root of x? Well, we already know the answer. It should be the positive square root of x. And then subtract 1, we get y equals the square root of x minus 1. And so f inverse is the positive square root of x minus 1. Okay. Earlier we observed that the range of f is from 0 to infinity. But we can also determine that the range of f is from 0 to infinity by finding the domain of f inverse. The domain of the square root of x is from 0 to infinity. So we have two ways of determining the range of f, or equivalently the domain of f inverse. So the domain of f inverse, to be a little more explicit, that's from 0 to infinity, including 0. And the range of f inverse is the same as the domain of f, and that was given to be from -1 to infinity. Okay, this is all that was asked. It didn't ask for a graph, but it might be worth the minute or two that it takes to graph f of x and f inverse. Okay, so for f of x, the smallest domain value is -1, and replace x with -1, you get 0. So at -1, 0, we have this point. The y-intercept, when x is 0, the y-intercept is 0, 1. So the graph of f of x with the restricted domain looks something like this. It's actually just a half of a parabola. And then to graph f inverse, the square root of x minus 1, well, when x is 0, we get a y-intercept of 0, -1. So we could also tell that this point is the ordered pair -1, 0. So on its inverse, we should have the point 0, -1. And this point, which is 0, 1 on f of x, we should have 1, 0 on its inverse. So there's the graph of f inverse. Okay, moving on, number 33. Given g of x equals 3 times e raised to the exponent x minus 4 plus 3, state the following. State the domain of g. Well, for this exponential function, we can replace x with any real number, and e to the x minus 4 is defined for all real numbers. So the domain is all real numbers from -infinity to +infinity. The range, however, we've seen enough of these to know that this has a horizontal asymptote at y equals 3. And the other values are, so if you exclude 3, these values, 3 times e to the x minus 4, are always positive. So the range is from 3 to infinity, but excluding 3. The equation of the asymptote, it's a horizontal asymptote, y equals 3. Horizontal asymptote. State the x-intercept. Well, there is none. There is no x-intercept. Just roughly, the graph is above the line y equals 3. So there is no x-intercept. The y-intercept, well, since 0 is in the domain, there has to be a y-intercept. So replace x with 0. The x-coordinate of the y-intercept is 0. And then replace x with 0 in the function. We just get a weird number, 3 times e to the -4 plus 3. Whatever that is. It's a number that's a little bit bigger than 3. Hey, number 34, sketch the graph of f of x equals the base 4 logarithm of x plus 4. Show all intercepts and asymptotes on the graph. Well, we should note that the domain, well, arguments have to be positive, so x plus 4 is greater than 0. So the domain is all x values greater than -4. So parenthesis -4, comma, infinity is the domain for this function. That's sort of important to know if you're going to graph it. And then the vertical asymptote is x equals -4. Okay, so we'll sketch a graph. So it's clear over here, x equals, whoops, sorry. I'll get another piece of paper. if I use pencil, I could erase it. Okay, so we're going to graph f of x equals log base 4 of x plus 4. So the vertical asymptote is x equals -4. And then we can plot a bunch of points. So if I pick x to be -3, the y-coordinate log base 4 of -3 plus 4 is log base 4 of 1. That's equal to 0. So this point, -3, 0, is the x-intercept. When x is 0, I have log base 4 of 4, and log base 4 of 4 is just 1. So 0, 1 is the y-intercept. So this is -3, 0, and 0, 1. And so we know the graph is going to do something like that. Okay, let's move on to the next part. Here, number 35, the mass of a radioactive substance follows a continuous exponential decay model. A sample of this radioactive substance has an initial mass of 325 kilograms and decreases continuously at a relative rate of 17% per day. Find the mass of the sample after 6 days. Do not round any intermediate computations and round your answer to the nearest tenth. Okay, so the way that we're going to interpret this, the expression continuous exponential decay model. So we're going to think of y equals y sub 0 times e to the kt. So the decay constant k has to be negative. I know that in some instances you'll see negative kt instead of just kt. Either way is okay as long as you're consistent. If I write it this way, I know that k itself has to be negative. Okay, so the initial quantity is 325, and if it's decreasing continuously at 17% per day, then the value of k is negative 0.17. Okay, so we can write the function y equals 325 times e to the negative 0.17 t, where t is measured in days. And so we want to find what the quantity is when t is 6. So when t is 6 days, the quantity y is 325 times e to the negative 0.17 times 6. So then you can key this into your calculator. So I'll dust off my calculator, and then we'll round it to the nearest tenth. So that's 1 decimal place. Okay, so if I did it correctly, I get 117.19. So if I round it to the nearest tenth, I get 117.2 kilograms. Okay, number 36. Solve the equations. Up here we have a exponential equation. 11 raised to the exponent negative x plus 9 equals 17 raised to the exponent 10x. So we'll just take the natural log of both sides. The natural log of 11 to the negative x plus 9 equals the natural log of 17 to the 10x. This exponent, negative x plus 9, is a binomial, so when you bring that exponent out front, you should put it in parentheses, negative x plus 9 in parentheses, times the natural log of 11. And on the right-hand side, we can bring 10x to the front and multiply 10x times the natural log of 17. On the left-hand side, distribute multiplication by the natural log of 11, so we get negative natural log of 11 times x plus 9 times the natural log of 11 equals 10x times the natural log of 17. We want to solve for x, so we need to have every term with x on one side of the equation and every term that doesn't have x on the opposite side. So if we just add the natural log of 11 times x, we'll get to that stage. So the left-hand side is 9 times the natural log of 11. On the right-hand side, we have 10x times the natural log of 17 plus the natural log of 11 times x. And then we'll factor x out of every term on the right-hand side. So 9 times the natural log of, 9 times the natural log of 11 equals x times 10 times the natural log of 17 plus the natural log of 11. And then divide both sides. So we get 9 times the natural log of 11 divided by 10 times the natural log of 17 plus the natural log of 11 equals x. Okay, this is what is meant by giving an exact answer. The exact answer could be made more compact, but this is good enough. Okay, now we have a logarithmic equation, log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. So since we're adding two base 5 logarithms, the first thing to do is write it as a single base 5 logarithm by multiplying the arguments, x plus 6 times x plus 2. And then we convert this logarithmic equation into an exponential equation. The base 5 raised to the power 1 equals the argument x plus 6 times x plus 2. So when we convert that, we get x plus 6 times x plus 2 equals 5 to the first. This equation is quadratic, so we'll solve a quadratic equation. So we get x squared plus 2x plus 6x for a total of plus 8x, and then plus 12 equals 5. Then subtract 5 from both sides. We get x squared plus 8x plus 7 equals 0. We can solve this by factoring easily enough. X plus 7 and x plus 1 equals 0. The quadratic equation has two solutions, x equals -7 and x equals -1. But remember, we're solving a logarithmic equation. When you test x equals -7, replace every x with -7, well, it only takes one negative argument to disqualify a number. So -7 makes both arguments negative, so -7 cannot be a solution. If we test x equals -1, this one looks like it will work. Replace every x with -1. -1 plus 6 is 5. And then plus log base 5 of -1 plus 2 is log base 5 of 1 equals 1. And then we have no violations so far, and then you can verify that this equation is true. So x equals -1 is the only solution to that equation. So I believe that's all there is to the sample final exam. But as I think I mentioned earlier that I found some other problems that different instructors used for the Chapter 3 material on their tests. So some of those are worthwhile looking at, I think. So let's try this one, if you can read it. Compute without a calculator. In the numerator, we have 3 times the base 7 log of 49 plus 4 times the base 4 logarithm of 2. In the denominator, log base 10 of 100 plus 4 times the base 4 logarithm of 8. So the numerator, 3 times log base 7 of 49. Log base 7 of 49 is 2 because 7 to the second power is 49. So this becomes 3 times 2. And then 4 times the base 4 logarithm of 2. The base 4 logarithm of 2 is 1/2 because 4 to the 1/2 is 2. So we can write this as plus 4 times 1/2. Then in the denominator, the first term in the denominator on the left, log base 10 of 100 is 2 because 10 to the second power equals 2. And then this one, well, what I'm going to do is I'm going to think of 4 as 2 times 2 times log base 4 of 8. And then we'll deal with that in a few seconds. So in the numerator, 3 times 2 is 6, and 4 times 1/2 is 2. Then in the denominator, I have 2. I'm going to use this 2 as an exponent on 8. So I have 2 times the base 4 logarithm of 8 to the second, but 8 to the second is 64. Okay, then in the next step, in the numerator, 6 plus 2 is 8. And in the denominator, I have 2 plus 2 times log base 4 of 64. Log base 4 of 64 is 3 because 4 to the third is 64. So this is 2 times 3. And then I get 8 divided by 2 plus 6, or 8 divided by 8 equals 1. Okay, the next one, solve the equation 4 to the exponent x minus 3 times 2 to the exponent x equals 40. This equation can be described as quadratic in form. It's not quadratic, but it's quadratic in form. So 4 to the x, that is equivalent to 2 raised to the 2x. So I'm going to rewrite this as I may have said that wrong. It's equivalent to 2, 2 to the 2x. And then minus 3 times 2x. And then I'm going to subtract 40 so that the right-hand side is 0. So just verify that 4 to the x is equal to 2 to the 2x. So think of 4 as 2 to the second. So 4 to the x is 2 to the second to the x. And then using properties of exponents, if you multiply the exponent x times the exponent 2, you get 2 to the 2x. If it helps, it would help if I wrote the correct term. This is 3 times 2 to the x. Okay, but you can use a substitution to make you can convert this equation that's quadratic in form into an actual quadratic equation. So the idea, if you pick a single letter to be the 2 to the x, then if I square u and I square 2 to the x, I get 2 to the 2x. So I can replace 2 to the 2x with u to the second, and then minus 3u minus 40. And then it might be easier to think about solving this quadratic equation for u. And then afterwards, remember that u is just a substitution for 2 to the x. Okay, so we can solve this one by factoring. One factor is u minus 8. The other factor is u plus 5. So this quadratic equation has 2 solutions. One is positive 8 and the other one is negative 5. Okay, but remember, this is just an intermediate maneuver. The goal is to solve the original equation for x. So now we put these 2 bits of information together. We found that u is equal to 8, so if we replace u with 8, in other words, 8 is equal to 2 to the x, and 8 is 2 to the third. If 2 to the third equals 2 to the x, then x equals 3 is a solution. You can verify that x equals 3 is a solution. In the original, 4 to the third is 64. 2 to the third is 8, so 3 times 8 is 24. And 64 minus 24 equals 30, so that checks out. Okay, but this other u value, negative 5, we replace this u with negative 5, we get negative 5 equals 2 to the x. But this can never be true. This has no solution. 2 to the x is positive for every real number x. So 2 to the x can never be negative 5. So this is false. Okay, so the only solution to that original equation is x equals 3. Okay, the next problem, well, we have less than 2 minutes, but we can solve this in 2 minutes. Use change of base formulas to compute without a calculator. So the trick here, we have 1 over log base 5 of 30 plus 1 over log base 6 of 30. So if we convert log base 5 of 30 if we express that using a the change of base and a base 30 logarithm, this becomes the base 30 logarithm of 30 divided by the base 30 logarithm of 5. And if this is in the denominator, then 1 over that is log base 30 of 5 divided by log base 30 of 30. And then similarly, this denominator, log base 6 of 30, use the change of base, convert this into an expression using log base 30. So log base 30 of 30 divided by log base 30 of 6. And then 1 divided by this, we have log base 30 of 6 divided by log base 30 of 30. Log base 30 of 30 is just 1 because 30 to the first power is 1. So these two denominators are 1, and I'm adding 2 base 30 logarithms, so I can write this as log base 30 of 5 times 6, or log base 30 of 30, and log base 30 of 30 is 1. So this just simplifies to 1. Okay, that's all we have time for today. On Friday, we will continue reviewing other problems.